Okay, hi, folks. I am Dr. Oliver Williams, and we are going to start on quite a venture today, and that is learning about biophysiological signals, or biosignals for short, and moving on and up to specifically to electroencephalography, EEG, in the uh, timeline of this course. We will just talk about the essence or basics of electroencephalography, and then we will move all the way up to toward the end of the course into doing hopefully even some statistical analysis of our brain waves to see if we can in fact induce or affect change in brain waves given a particular state of mind or given a particular exogenous state, or in other words, whether it's noisy or quiet outside, whether it is light or dark, and so on. So we're just going to look at the basics first and then move on from there. But before we understand what biophysiological signals are, we need to first of all understand what signals are, exactly what it is, and where they come from. And wherever they come from, how are they produced? So we're going to really start, first of all, with just the very basics of biophysiological signals, and then move on into what they mean and how we can observe and analyze and conduct experiments using them. So one of the first things that we encounter using looking at biosignals or biophysiological signals are if they're used now everywhere. Now, mind you, this has just started. This has just been in the last 100 years or less, even maybe 90 years. But now we use basic biophysiological signals everywhere from medicine, motion control. We look at it. We use wearable sensors and systems. If any of you have an iWatch or some other technology that gives you feedback on your physical status, that is measuring biophysiological signals that watch. So we use it in monitoring, telemetry. We can monitor the very essentials of some of the life emitting processes simply by looking at biosignals. And these are being used more and more and more every month, every year as we progress and as the technology improves in order to allow us to facilitate the merger of technology and electronics to biology. And this is really essentially what we're doing, is that in this sense we're measuring, but we also use biosignals to implant technology, and then gather the signals from the implanted technology. So think science fiction, think cyborgs. Hey, you might even think eventually androids, and hey, Westworld or Mr. Data or Commander Data, that is in Star Trek. But we are, of course, I'm being a bit hyperbolic in saying that, but we are in essentially moving in that direction. So what are biophysiological signals? What is their origins? They are generated by nerves and muscle cells, but they are generated specifically by our biological basis, nerves and cells that operate via electrochemical activity. So to some degree, we'll also look at that electrochemical activity and just how does that produce a wave. So this is one of the essential areas that we will examine somewhat briefly, but examine it nevertheless to arrive at what an EEG, what a brain wave is. They can be measured, and they can be measured with either intracellular or extracellular electrodes. Or in other words, we can even go inside a single cell and measure the activity as well. I remember as a graduate student at University of California at Irvine, I was studying biopsychology, or actually psychobiology. And my job as a graduate student assistant working in a research lab was to measure the speed of the action potential starting at the head of a flatworm and ending at its tail. Now, of course, the first job there is just to determine where the head and the tail is on a flatworm. But then after that, we had such precise electrodes that it could, of course, under a microscope, that the electrode pipette could be inserted into the very one end of the flatworm's notochord. It's not really a spinal cord, but a notochord, and the other end, and we could. Or I was measuring the just simply the speed of the action potential going down that particular species of flatworm, which, as I remember, was called Notoplana octicola, and it was the first extant organism with a notochord. So that is, for example, is an example of intracellular measurements in other organisms. We often do that surgically with humans as well in order to determine exactly where certain problems are originating. We and some of the types of physiological biosignals include ECG, electrocardiograms, and EGG, and EEG, and EMG. All of these are, let's see, what is ECG is electrocardiogram, EGG is electrogalvanomic graph. EEG, of course, you know what that is. EMG is myography, myograph, in other words, the signal that comes off of muscles. So there are those and many, many other different types of physiological signals that we can detect from our bodies and from the bodies of any organism. So where did all this start? These signals, they continuously pass through various parts of the body, as you can see here in this diagram. And I wanted to put that up there just to illustrate that these processes and the measurement of such sort of go hand in hand with the advancement of science and technology. And so much of this did not start until the turn of the 20th century. They are, of course, again, and I'm going to emphasize this over and over, carried by electrical energy, nervous system, certain molecular signals in our endocrine systems, other types of biological processes. But this is really fundamental to diagnostic medicine, bioengineering research, and of course what we're doing now, and it's becoming even more and more important in the field of treatments in clinical psychology and also in research. Biosignals have become much more important and prevalent in the treatment of psychopathology. So a biosignal, again, any signal, usually electrical in origin, of a biological origin. So what do we say? Well, bioelectrical signals, and again, this is we've talked about this already. Electroencephalogram, electrocardiogram, a myogram, mechanomyogram is used quite a bit. In fact, when you've seen movies and games where the animated figures appear to just be human. They have natural motion. And those are done by brilliant game designers who put who use humans to move around, and then they track their electromyograms as well as their points in space where they attach different dots to their bodies in order to get an idea of motion in space. And like I said, they also use mechanomyograms to do that as well. Electroencephalography is the is looking at the signals that are coming from the eye, and then galvanic skin response. I'll give you some demonstrations of all of this during the course of this presentation. Some non-electrical biosignals are mechanical signals and acoustical signals, chemical signals, optical signals. Eventually, those do eventually become electrical signals as they are sensed and then processed by one's decrypting system, one's brain, and other intermediary decrypting or intermediary cellular processes prior to reaching the brain. So one thing about a biosignal is that they have a time domain characterization. What does that mean? That means is as we go through time, they go up and down and up and down. They have a certain periodicity. So so you start at time 1 and then you're measuring the biosignal. You'll see that it changes as we go through time. So we see that they have periodicity of two types. They're either periodic, which means that they have a regular shape, constantly going up, going down, going up, going down, or at least some reasonably repeatable shape going back and forth, or aperiodic signals where the shape of the signal never really repeats completely. Now, in that we aren't precise and exact frequency generators, we sort of are really sort of in the mid-ground there. Most of our signals are half periodic and half aperiodic. You might think of some very periodic signals that we don't want to change a lot, in fact, as being, for example, an electrocardiogram. It is basically periodic, although you will see, very slight variations in any ECG going from beat to beat to beat. The other thing is that there's a certain amount of predictability in a biosignal. Now, predictability can be either on the deterministic side, where the signal is in fact predictable for a certain time span of interest, or they could be random, which would suggest that the signal values cannot really precisely be anticipated. Now, of course, one of the reasons for research is that we are able to experiment with situations and with phenomenon where we learn, develop theories, and then make predictions based upon those theories. So indeed, to some degree, what we consider to be random may not be completely random. Now, you'll find that EEG has both periodic and aperiodic characteristics, of which we will look at as well. So I think most of our biosignals are considered down there in the bottom there. What are quasi periodic? An ECG, for example, is quasi periodic, measuring blood pressure. Diastolic, systolic, diastolic, systolic, diastolic, systolic. That is quasi-periodic. It doesn't go, it isn't random, and luckily for us, they're not random. But most biosignals are somewhat aperiodic and non-stationary. That is, they move. As any wave moves, they are waves essentially, and we're going to get into the exact nature of those waves as we continue through the course. So biosignals that we measure originate from electroactivity from neurons in the associated organ, and these are really the types of biosignals that we're going to be most interested in, and those are the types of biosignals that do originate in neurons. And in fact, neurons, our nervous system is almost completely electrical, or rather electrochemical. So we'll take a closer look at that. But here in this slide that I've got up here, you see that there's the heart with the very characteristic looking biosignal, the ECG, the EMG, the electromyograph, the motor unit also, and a motor neuron. Those are all basic. We can get signals from there. We get signals from heart rate and respiration. And then in the lower left-hand corner of the slide, you see the two Velcro-contained electrodes on the fingers. I'm going to show you that in considerably more detail later during this presentation. So we've looked at here, we look at the biosignals from these various organs and substrates, but how about biosignals from the brain? And I think that's why we're all here anyway, to find out what those are all about and how we read those. Now, those are very special signals for many different reasons. So let's look at how those signals are produced. That is, where do they come from? How are they produced? Why are they there? How can we read them? What is the origin and composition of a brainwave, an electroencephalograph? Now, we know that pretty much all organs are innervated by neurons, and neurons are electrochemical by their very nature. Without this turning into a full-blown discussion of biopsychology or psychobiology, in which we would get somewhat into the details of the neuron, not only the action of the neuron, but the physiology and anatomy of the neuron as well. We do need to understand just essentially how a neuron works, because again, we're going to be observing and measuring electrical signals from the brain, and the brain is billions of neurons. So how do we do that? Well, first of all, we need to understand exactly how that wave, that energy, is produced. We can't just randomly toss around the word energy, or at least I don't think we should, unless you understand the energy itself and what that energy is. I mean, the energy can be the energy of motion, we call kinetic energy. It can be electromagnetic energy, which we're going to get into in some detail, which is the energy comprising a wave moving through space and perpendicular to it a magnetic field as well. We don't want to study that a lot because I don't want to make a physics course out of this, but in order to generate the primary energy of the axon, the energy that we're going to really be studying for EEGs, we need to know where that comes from. And that comes from an interchange of sodium and potassium ions across the membrane of the axon itself. And so that interchange that creates a wave, essentially, a wave that moves down the axon. So here you see here's a neuron right here, and here's the axon. The long part of this is the axon, and here we have dendrites. We have the cell body or soma here, and out here we have what are called the neuron buttons. So let's say that a signal comes into here, and the axon is fired, so that the action potential is now created and moves down the length of the axon off into these neuron buttons. And these neuron buttons you don't see here, but they would also then connect to other dendrites from another neuron over here, and then they would either tell that neuron to be excited or to keep it cool, one way or the other, excitation or inhibition. So neurons produce electrical energy, and that electrical energy is a moving charge. and concomitant electric fields by shifting the electrochemical balance of its cellular structure, as it says there. But what that means is that the action potential, the electrical action along the neuron, how it goes from the soma, the cell body, down to the buttons to transmit information to other neurons, is done through a wave of constant interchange of sodium and potassium ions across the cell body, and that creates an imbalance. Remember that it is the goal of nature to reach equilibrium, and so this imbalance sends out this wave down the length of the neuron. That wave is called an action potential, and so anytime we have a moving charge, something amazing happens. I'll talk about that moving charge here in a second. Now, I need to stop and mention that I really do wish that I were in front of you all demonstrating this instead of on this video, because part of this demonstration and part of this presentation, that is really also to spur your questions and your imagination. And I get quite a charge from students who ask questions, and I see that their imagination and their research interest is spurred as well. So we don't have that opportunity to have that kind of interaction here on this in our current dilemma of having to maintain social distancing and not being able to get together in a room and talk and listen. So I think that you're gonna have to bear with me on this, and bear with everybody else, because this material in and of itself would be something that I'm sure many people would certainly have questions about. So then we'd stop and start and stop and start. I know that anybody who has had a lecture, especially at a lecture with me, and especially at the intensive, knows that as people ask questions, we sort of go off on tangents, but get back to the point anyway, nevertheless, to what the subject matter is. So this is a new course, and it is a course I am very excited about. But again, this is an area where you guys are looking at this, and I'm not getting any feedback because I'm not there with you. So as I talk about this, I like hear your questions going on, not in a psychotic manner, of course, but in an imaginative manner. I do hear your questions going on. The voices are gone. They went a long time ago after all those meds. No, I'm kidding. So what do we have here? Now, remember, I mentioned here that we can have when the signal, the action potential, moves down this axon and here into the buttons of the neuron. As it gets down there, these can either, depending upon the purpose of this neuron, these can either excite or inhibit the next neuron to have an action potential. And so we have synapses, that is the junction between the button and the dendrite or the cell body. We can have action potentials that either excite the receiving or adjacent neuron or inhibit the adjacent neuron. And so sometimes when we have enough excitatory, we have both excitatory and inhibitory responses, we need to, it is literally a summation game. If the number of excitatory responses exceeds the number of inhibitory responses in order to generate a signal, then the signal would be generated. If there's too much inhibition and not enough excitation, then of course the signal won't be generated. But here we see this here we see our excitatory potentials and inhibitory potentials, both here. And we see that here's the membrane potential in millivolts. So the membrane is in fact the voltage that we see going across the axon. If we were to measure that, if we measure that as we often is done many times, you could see over here that is, here we see an excitatory enough excitatory potential to then start the action potential, and then it goes down slightly, and then it goes back to baseline. So it goes back to baseline until we have enough energy to say, okay, fire. Go ahead and fire. And this is replicated in our nervous system right now as you sit there and listen, or as I'm talking, billions and billions of times per second. So without trying to beat this to death, this is really some of the most important part of what we're doing here is where do those signals come from? Because if you're measuring something, you at least need to know where it's coming from and what's doing it. So we see here the cell body, the dendrites, here's the axon, and here are the terminal branches or terminal buttons of the axon right here. And so we see the axon of the previous neurons right here, those buttons then interact with the neuron, the cell body of an adjacent or coupled neuron that then, so here those interact with those dendrites to either create or inhibit an action potential to then go down to the next neuron and so forth. So it is an extremely complex process. When we have a current or charge moving, a moving charge, and in fact that's what a current is. It is a moving charge. If you take anything that's charged, if you charge up a bunch of ping pong balls and move them very quickly through a pipe, and then you were to measure the magnetic field around let's say you're running those ping pong balls through, let's say, a 3-inch plastic pipe. And then so you start pushing charged ping pong balls faster and faster through that non-metallic pipe. If you if you were to measure the magnetic field around the pipe, around that plastic, you'd see a magnetic field. And you would also see a stronger and stronger magnetic field as the speed of the ping pong balls proceed through the pipe. Well, in the same way, the charge moving down through the axon is in fact like the ping pong balls, and that creates a magnetic field around the axon. So in the same way that you would get a magnetic field by running ping pong balls through a pipe, or the same way that we see a magnetic field around any wire in any of your household appliances, because instead of ping pong balls, those are electrons, and electrons are being forced through a pipe, the wire in this case. You see a magnetic field around that. And in fact, that is the essence of how a generator and a motor work, is by the interchange of magnetic field and electric field, the association between the magnetic field and moving charges going through. So we can detect and measure signals with instrumentation. Obviously, we know that. We can use all different types of instrumentation to measure these fields. Now, of course, in a biological system, we are a bit inhibited in trying to measure the fields or even knowing where to measure those fields. But we can detect and measure these signals. And again, remember, this is relatively new, like within the last 100 years, because before that, we didn't even know about the relationship between electric fields and magnetic fields. We didn't know how to measure anything. We didn't know even what an action potential is. We didn't know what to measure. We didn't even know it was there to measure. So we can indeed measure a single action potential. And like I told you at the beginning of this thing, in order to torture graduate assistants, as I was once in psychobiology, I was measuring the speed of an action potential and also the amplitude of the action potential as it made its way down the notochord of Notoplana acticola, the flatworm, and literally, essentially doing exactly this, what that hand is doing, where there was a measure here, not a single axon, but in fact a notochord, which was made of several axons, but I could measure the speed of the potential moving down the notochord. Here is essentially the same thing, and here we see we're at a resting potential. The neuron is normally at a resting potential of about negative 70 millivolts. A millivolt is 1/1000th of a volt. So this is normally resting at about negative 70 millivolts. And essentially, it gets to the point if it has enough excitatory signals, if the neuron gets enough excitatory signals, it pushes it above negative 55. And if it goes above negative 55, it becomes depolarized. And if it becomes depolarized now, it goes up to plus 40 or so. And we can see this transverse, it's polarized and then it drops off. Then it becomes hyperpolarized down here. That's called the refractory period. And then it goes back to negative 70, of course, unless there's another one coming in very quickly. Now, this can only go at a certain speed because during the refractory period of an action potential, nothing will make it go any faster. It has to have that refractory period before it fires again. So as I have been harping in the last 100 years, and actually more specifically in the last 40, 50 years, we've created more and more sensitive detection technology, because we may know, we may uncover truths that have been hidden from us in nature, but in order to examine it better and better, we need to have more sensitive technologies, and they seem to go hand in hand. And that is, the more we research and discover in science, the technology comes along, uses that information to create even more sensitive technology. One of the things that technology has done for us, if not really the only thing technology has done for us, is that it has increased our ability to sense the world, because our ability to sense is very limited to that which has allowed us to survive. So we only see a very, very small part of the electromagnetic spectrum. We can only hear a very, very small region of audible hearing. We can only feel certain things. We can only smell certain things, and so on. So we can use, and we do use, technology in order to expand our limits so that we can look out into the universe to see electromagnetic energy that is not of the visible range, but energy from ultraviolet, from microwaves, from radio waves and gamma rays, and even X-rays, all coming from the universe. We have specialized detection equipment and satellites that go out there and see and send back to us and transduce those images taken in spectrums that we couldn't see merely with our naked senses. We can transduce those with technology. With technology, we have also been able to convert analog frequency, and that is just like a brainwave is analog, or anything, a disc, not LP vinyl record, that was analog. The CD disc is digital. Film, analog. DVD or Blu-ray, digital. Our ability to sense any and all of these things do come from more and more advanced technology. So when we look at any kind of a biosignal, recording signal, we have electrical activity. And in recording that electrical activity, we now especially need to turn the bioelectrical activity, which is always analog. We are not digital creatures. Turn that analog into digital energy. And so as you can see here, when I've got here, this analog signal is coming in. Now, how do we change that analog signal into a digital signal? And this is another important area that we've now gotten into in technology. We can take analog signals, convert those to digital signals, as much and therefore create a digital substrate that we can analyze. Human history, as we have looked up into the stars, as we have looked at fire and did not know what that was whatsoever, nor did we know why that saber-tooth was chasing us, but it is. What does it have against me? All of these things we didn't have answers to. We didn't experiment. So we thought around, and thought about it, and the wisest of us came up with what seemed to be then rational ideas, but those weren't based on experimentation. Those were based upon, this makes sense because that's all I can see. Like the Earth looks flat, but it isn't. Everything looks like it's going around the Earth, but it isn't. So all of the great minds from the last 10,000 years, but especially prior to a couple hundred years ago, believed exactly what they saw. And I mean, believed, and too much to their credit, were able to use logic and reason in order to make sense of what they saw in the world. But unfortunately, logic and reason and rationale isn't enough. One also then needs to apply that logic and reason to induction. That is, I see this again and this again and this again. What if I do this, this, and this now? Then what changes? And that was something that we didn't do. We didn't really experiment. We didn't have good experimental methods. And so because of that, I've just got here some of the many things that we've overcome, like the Earth being the center of the universe, and oh yes, bloodletting. That was a good one. Earth, water, fire, and air being the four elements of the Earth. And if you can go to any periodic table and see that there are, in fact, 92 natural elements, and then beyond that, we've created quite a few elements of our own simply by smashing more protons and neutrons into a nucleus. We have the four humors. Was medical science at the time, so a combination of using the four humors and bloodletting, plus some other techniques that they had in medicine then, were meant to treat sick individuals. There was absolutely no idea of what bacteria and viruses were at the time, and so they did the best that they could based upon what they had. Ships going off the edge of the Earth because, of course, the Earth is flat. Galileo demonstrating that gravity acts on all mass exactly the same way, whether it's whatever it's made of, whether it's made of gold or lead or tin, or whether it's heavy or light, taking in consideration air resistance. If you have a perfect vacuum, I've done this experiment, seen it in physics labs many times. If you take a vacuum bell, and inside you have a feather and a lead ball, and in that vacuum you drop both the feather and the lead ball exactly at the same time, they will both hit the bottom, the surface, the table, at exactly the same time, even though the feather weighs a lot more than the lead ball. It's irrelevant. Gravity acts on both of those masses exactly the same. And if you get rid of the impeding characteristic of air, that is in a vacuum, that's what you see. So how do we demystify observations? How do we make sure that our experiences, which all of these great minds in the past had experiences, but they just didn't know enough to accurately interpret what that experience was, and hence could not make accurate predictions based upon their experiences. They used the best that they had in order to come up with the answers that they got. So I think one of those early contortions of reality was Scientology's E-meter. I don't know if any of you have seen or have been approached by Scientologists peddling their thoughts and wares, but what they have you do is come along and you can see these two cylinders in his hands, and you see the instrumentation here. Here's the instrument, Scientology's E-meter. Well, that E-meter is just a simple, basic galvanometer. And I made my own E-meter. I'm going to show you how that works right now with my own E-meter.
So Scientology had used or saw that galvanometers, or in other words, skin conductance, was a measure of stress, and so they put out all of these get your stress test for free using their so-called E-meter, which is really a galvanometer, which is reading skin conductance. Now we all know, as we are sophisticated graduate students, that stress and consequently skin conductance is a measure of the autonomic nervous system, and more specifically the sympathetic nervous system, which controls the amount of stress that one feels, and also the amount of cortisol that is in one's bloodstream. But one's stress levels, and hence one's galvanic skin response or electrodermal response, goes up and down instantaneously almost from moment to moment based upon the kind of anxiety and stress that we feel. One of the components of a polygraph test, so-called lie detector test, is in fact galvanic skin response or galvanic skin conductance, which we're going to see later. But as an answer to just the Scientology's E-meter, which was a contortion of just some basic science and physiological response, I said, gee whiz, those things cost $3,000, $4,000, $5,000, $6,000. I think I could make one a lot cheaper and really demonstrate what it does. So that's what I'm going to do right now. And what I did was went on to Amazon and I bought just a basic multimeter that you can measure voltage in amperes and resistance, which is measured in something called ohms, O-H-M-S. And if you Google it up and look for Ohm's law, you'll see the relationship between resistance, current, and voltage. So, but we're going to measure skin resistance, and skin resistance, i.e. galvanic skin response, is in fact measured in ohms. So I bought this meter, and this meter has a nice function in that it is also able to measure not only skin conductance, but also it came with a little application so that we can actually see it on the screen and even record response. So I've got this, and we've just got to set this up now a bit. So I'm going to connect the multimeter into the computer. This connects into our computer here, like that. And so we can set this up like this. And so now we've got that set up. And now what we're going to do is, the Scientology have very finely machined brass holders for you. Well, I just took a couple of Campbell soup cans and cleaned them up a bit. I'm taking some old jumper wires, and I'm going to use these jumper wires here and connect those to the multimeter's terminals. By the way, this multimeter I think cost me $50 or less. And the tin cans cost whatever the tin cans cost. Get these terminals in there, like this. That one goes in there like that. And we are about ready to go. Now I'm just going to connect these terminals to the tin can. For tin cans, there's one. And the other one goes onto here, like that. So now we're connected to the tin cans. Now we have to make sure that our multimeter works. So let's go into here, and the program that makes this work is right here. A little tiny program that works here. And I wish I could make that a little larger, but it's not. Now the first thing I have to do is set this up so that it is reading the correct port, because it doesn't always read the correct port initially. And so what do we have here? We've got COM port 4. Let's see if that does it. And if we start, aha, that's it. Usually doesn't work the first time. Okay, so now we've got this going on COM port 4. And now notice that when I pick these up and turn this on, okay, so notice that if I just connect or connect the two leads together, there should be no resistance because they're in common contact with one another, and they're both conductors. And you can see on here that it goes to 0. And we're going to look here now and turn on our system as well. So we're going to start. And now this is measuring. You can see that, and you can see that the when I do that you can see that the digits go to 0 ohms or close to it, and the meter, of course, goes to 0 as well. And then when I release it, there is no connection, and it goes to completely nothing. There's no conductance at all. Now that's measuring. In that case, it's measuring megohms or millions of ohms, and it's way more than several million ohms between these two leads here, because there's no conductance. And then again, when I touch them together, it's 0. Now, what if instead we hold each tin can, or excuse me, E-meter conductor. So as I hold this, now you can see that that's my skin conductance varying, and the variation is really due to my pressure in holding that. If I release one, of course it goes to absolute resistance, pretty much. In megohms, it won't register because there's no conductance at all. But now as it's going through my body, through my skin, it's measuring that. But if I release the pressure even on the cans, it changes. And so I could really change my stress level just by squeezing hard or soft on these cans, and that gives you a stress level. And there's probably a correlation between somebody who's under stress and squeezing soft or squeezing hard. So I think what those e-meters were measuring is not so much stress, but somebody who's squeezing hard or soft. So it's not if somebody's, and there's probably a correlation and maybe a reasonable, moderate correlation between the two, between squeezing something hard, squeezing something soft, somebody under stress, somebody not under stress. But at least the idea here is that you understand that what we're measuring here is skin conductance, and in some ways that is measuring stress, but this is a far too uncontrolled system for doing that. So now we're going to, in the next, so now what I'm going to do is show you a more sophisticated type of polygraph that does in fact use skin conductance. It uses respiration and also pulse rate. So now these are three different biological signals that are being processed through a computer and that we can measure. And then from that we're going to go into even more complex biological signals, i.e. our brain signals, where they come from and how we measure those.
So we saw how that homemade e-meter, Scientology e-meter works. It's just a basic galvanometer. It's essentially an ohm meter. I won't go into what ohm meters are and the relationship between resistance, current, and voltage, but that really is what it is. And galvanometers have been around for a while, maybe even a little over 100 years, maybe 120, 130 years, galvanometers. Maybe even earlier than that. I don't know the history of galvanometers, but they're basically pretty simple measuring device that can measure that measures resistance. And in this case, we're measuring what's called galvanic skin response. Now, a more updated version of GSR is EDR, electrodermal response, and that's really what the polygraph is all about, plus some other things. So in moving now from this polygraph, we move into just other types of biophysiological methods, and we're going to sort of separate those into two categories. Although, as categories go, there's a lot of gray area in between. Nothing is just purely demarked one or the other. So in vivo biophysiological methods include processes of looking at internal responses and measures within a living organism, and we can do that through medical, surgical instruments, lots of different methods in which that are essentially intrusive, and that is we stick something in you and then measure it from there. Now we've gotten more and more into non-intrusive measurement and observation. Enter all of the brain imaging technology that we have today that would have been absolutely impossible, I think maybe even like 30, 40 years ago, especially given the rate of technology and some of the scientific discoveries that have just happened within the past 5 or 10 years. The other amazing types of brain imaging and other internal types of imaging that we can then gather now through new discoveries and new advances. So in vivo, that is directly in the organism, versus in vitro, which are physiological processes that we measure outside the organism. Or in other words, they're non-intrusive. So for example, the X-ray, it's wonderful. So instead of So to find out whether or not you've got a broken arm, or let's say a microfracture, we can take an X-ray. And we don't have to open you up and pull all your skin and muscle back in order to look at it to find that out. We take an X-ray. A CT scan or computer tomography is simply it's another form of X-ray, but it's X-ray in slices in combination with computing, so that those slices are then put together by a complex algorithm in order to create a three-dimensional representation of your brain. Of course, MRI, PET scanning, lots of other in vitro type tests that are non-intrusive. When we look at different types of measures, and I've got 4 up here that we can look at. First of all, A is the ECG, the electrocardiogram, right here. And that looks very regular. It's very periodic. But then again, notice that we've got it's periodic, but it's not exact. So it's far more periodic than it is aperiodic. Versus over here, we're looking at an EEG, that which we're going to eventually get into exclusively, and you can see here that it's certainly not as periodic, anywhere near as periodic as an ECG, but there's some periodicity there. And we will talk about how we extract through technology and through a process of statistical computing, on-the-fly statistical computing called a fast Fourier transform analysis. We can actually get the wave characteristics even of the EEG. Very, very, very important technology in doing that. Down here on C is the electromyograph. So this is showing muscle activity. Now, there's muscle activity all the time. Just staying still means that there's muscle activity. Anything requires some electrical signal to keep the muscle exactly where it is, even requires an electrical signal. And then there's EOG, electrooculography, and again, that is a method of looking at the stability, the ocular or photonic stability of the eye. So we can put all of these together, and somebody said, well, gee, what is it about galvanic skin response and some of these other processes? For example, if somebody feels anxiety, anxiety is a result of your autonomic nervous system triggering your sympathetic nervous system, which is part of your autonomic nervous system, and it's tied directly to that fight-flight response. And that fight-flight response, again, it's not one or the other, and it is in gradations, going from very small to very large. But if we have the instrumentation to look at that, indeed we can measure even small deviations of the autonomic nervous system affecting our other organs, including our skin and our hair, which is your hair standing up on end is called piloerection. Your pupillary responses, whether they get dilated or constricted, and our good friend GSR, galvanic skin response, or EDR in the case of a polygraph, where your skin does indeed change its resistivity relative to very small variations in anxiety. And many, though not all, will evince changes in their autonomic nervous system, which then affect parts of your body that we can, in fact, measure non-intrusively. So we now then go to a more advanced digital polygraph system, where all of these different measures can be measured and looked at. But we will get into not quite EEG yet, but we will get into studying that EEG and how these work as well. That's the polygraph. So now I also have a polygraph that I can show you, and what I did was we've got this very, very simple, very basic polygraph, and so we can look at three things with that. We can look at electrodermal response. We can look at respiration and breath jitter as well. So, and we can look at pulse or heart rate, because clearly, like if you feel anxious all the way up to a point where you feel scared, your heart rate jumps up. And again, if you've ever gone into your physician's office, or even if you have your own blood pressure monitor, you can, if you feel anxious, your blood pressure is going to be a little higher than not feeling anxious. You try to sort of, like, if you're going to go in and get your blood pressure measured, you want to sort of sit there and relax, maybe close your eyes, and you find that your blood pressure is not quite as high as it would have been otherwise. So this thing I'm going to show you right now is a very simple polygraph, but we've hooked it up through the computer, and I'll show you how that works now in this next demonstration.
Last time, an example of a very simple biophysiological measurement that wasn't very well controlled, in that we didn't control the pressure on the skin, we didn't control the distance the two electrodes are apart, and that was the only reading that we got, was that simple galvanomic response, or in other words, the one skin resistance, which we call a galvanic skin response, or electrodermal response. So now we're going to look at some other biophysiological responses, not up to EEG quite yet. But what we're going to do now is I'm going to attach a basic polygraph to my lovely wife here, and then I'm going to ask her some questions to see whether or not she's been lying to me our entire 27 years of marriage. So, no, not really. But what we are going to do is just look at the different responses. So we're going to look at three things here. We are going to look at a galvanic skin response, only we're going to look at it, though, as a function of having a more exact control in it. Because remember, whenever you do take these, take any kind of physiological measurement, or any measurement for that matter, even a psychological test, it still have to be always under similar conditions. If you do any test under different conditions than the first one, then your exogenous variables, that is everything that's on the outside, can change what you're measuring. So we need to make certain that we have as much accurate instrumentation as possible. So here, let's hook Irmgard up. Are you okay, Irmgard?
Oh, yes.
Okay. So here's what we're going to do. First, I'm going to connect her with this. This measures breath rate and breath pattern. So I put this around her abdomen right here, like this. And let's see how this works. There's a lot of wires and straps here. And you know, if you're in the CIA or something like that, you got to go through this all the time. And the strap has to go around her abdomen, so that it's snug and measurable. That okay, I'm good?
Oh, yeah.
Okay, I'm going to make it a little snugger, like that.
Mm-hmm. That's fine.
Is that okay?
That's good.
Okay, so now we're going to put that there. Now, can I see your left hand?
Yes.
Okay, and on her left hand, we're going to do the two galvanic skin responses here. And so I'm going to take her index, her lovely hand, and her lovely index finger and middle finger,
And so I'm going to put this around her index finger like this, nice and tight. And then I'm going to put this around her, oops, it really should be on the outside. Oh, it is on the outside. Okay. And then we'll put this around her middle finger, like that. Like that. Okay, so now, is that comfortable?
It's good.
Okay, and then we're going to put this is a ground reference point, we're going to put that just right there on that finger like that. So we got that. So now we're set up here. A line right there is simply indicates that we are in fact connected, but also that's her galvanic skin response. And the blue line is simply her breath jitter, and you can see that that's fairly stable. The red line is her pulse, which is reading 94 beats per minute right now, 94, and her galvanic skin response. Back to me. So I'm going to ask her maybe a couple of questions, like just yes and no questions. Is your name Imgard?
Yes.
And if we look at the green line, there wasn't much of an anything. Are you from Canada?
Yes.
So in that, you could see there that just from that question that we got a bit of a rise there. Now remember, this is no kind of professional setup or not, and I'm just showing you this just to give you a feeling for what biophysiological measures are and various biometric measures as well. But it all started with this and this technology, and even this technology wasn't around 100 years ago. EEG is far more complex to measure, far more sensitive, and the technology, the amplifiers that we use in order to take an EEG measurement have to be not only very sensitive, but also have to be very good at noise filtering. So we can see here that she's stable. Here we've got her line, and she's got a very stable pulse rate. Her galvanic skin response is very stable, not changing much. And her breath jitter, as you can see also on the blue line, is also very stable. So with that in mind, I know you were hoping to maybe catch Imgard in some false statement, but she's very honest and very forthright, and she hardly never lies. Do you, Imgard?
Yes.
You do? Really? When is that? Look at that. So you do lie. Okay, now you see the response that we got based just upon that interaction. So with that in mind, we're gonna cut this short, and that's now the piece on biophysiological measures. And so the next thing we're going to look at is a live EEG using your Muse 2 headbands. And what we'll do now is hook later in the next video, is hook that up. I'll show you the best way to hook it up because I had to do some experimenting with it to find a place where you get the best maximum contact.
So in seeing how our very basic polygraph works, and indeed that was a very basic one, and polygraph tests, as you probably know, are not 100% accurate, reliable, or effective. First of all, you need to have a conscience. And an individual who has trained himself, that certain behaviors, like lying, is not something that is unconscionable. You would not feel any anxiety in a lie. So, and that of course would really apply to somebody who doesn't have to teach themselves that, like somebody with antisocial personality disorder. Whatever they say, whether that individual says is not subject to moral and therefore autonomic filtration. So consequently, no autonomic response. But you can also be trained to not have any autonomic response and therefore fool, quote unquote, fool the polygraph in the same way that you can do very basic biofeedback. And in fact, that's where biofeedback first started, is with these basic responses. You can train yourself to have a lower blood pressure, a lower respiration rate, a lower galvanic skin response. And so there are training procedures, not just distraction procedures, but real training procedures that you can get around that. Now, of course, more advanced equipment and technology can even look at whether or not certain methodologies being employed to get around the polygraph. But generally speaking, they are still not extremely reliable. They are somewhat reliable, but on the other hand, there's too many false positives and false negatives to rely on them 100%. They're useful in some situations. Certainly they're useful in situations where you want to know something, and given the results, it doesn't say absolutely that this individual is telling the truth or telling a lie, but it can at least provide enough stimulus in order to investigate further. So in that we've looked at the polygraph, let's now turn our attention to the EEG, the electroencephalograph. What are the primary hurdles in EEG measurement? Well, first of all, the human EEG signal, that which can be detected, is anywhere from 10 to 100 microvolts in amplitude, as measured from the scalp. Now, a microvolt is 1/1,000,000th of a volt. So detecting that signal and discriminating that signal from anything else is we have a two-stage process. First of all, we need to detect it. Actually, it's a three-stage process. First of all, detect it. How do you detect a signal that is in the millionths of a volt? How do you detect that? How do you have a sensor that will detect that small of a signal? Then the next process then is amplifying that signal. So let's say it's a millionth of a volt or 10 millionths of a volt. How do you amplify that in a manner so that it is now readable and representable to our senses? How can you take that same signal and amplify it so that it will drive an indicator or a polygraph pen or an ink pen or sensors in a computer that, given certain inputs, will cause the monitor or the screen to respond in a certain way? We have to amplify it. And third, and this actually is the most difficult. We've already had two difficult problems with that. A, sensing. B, amplifying. Third, we have what's called a signal to noise problem, and we'll get into that in a minute. But as you can see here, we have a small signal in, an amplifier, and a larger signal out. So that's a lot easier said than done. Where have we come with amplifiers? Just only with amplifiers? Well, we've had first of all vacuum tube amplifiers, and for those of you who are old enough to remember vacuum tubes at all, there were no transistor televisions. There's no transistor anything. In fact, one of the first consumer type products with transistors were transistor radios. But before that, everything had vacuum tubes, and vacuum tubes got hot. They were large, and they got hot. All of our televisions, I think probably up through the 70s, maybe even going into the early 80s, were all vacuum tubes. I can tell you, when I was a student getting my bachelor's degree at UCLA, and I had a side business as a TV repairman. And so I drove all over Los Angeles, had a little business going called Rapid TV Repair. And I drove all over Los Angeles in my van, uh, fixing TVs in their house when I could, or taking them to the shop. And that was no small ordeal. TVs were not light. They were very, very heavy. I had to carry a dolly around. Sometimes I had to take a helper. And a lot of it was the tube. And so a lot of customers, uh, uh, when you walk in the door, one of the first things you have to fight off is, all you have to do is put a tube in it, and it'll fix everything. And that was true maybe 40% of the time. The other 60% of the time, it was something that was a little more serious problem. And when those serious types of problems occurred, you had to take the TV out, put it in your van, then take the TV back to your shop, take the electronics, the console of the television, because televisions were big pieces of furniture a lot of times. Take the console out, put it up on your bench, and analyze it. But sometimes I carried around a big box, a tube caddy filled with different common tubes that could be used, and you could replace those in the field. So at first we had vacuum tube amplifiers. My first job as a teenager was as a computer operator working for Northern Natural Gas. And what I did was I loaded the computer mainframe. There's no such thing as a PC then. I loaded the mainframe computer, occupied a very large room with a false floor with hundreds of cables going back and forth in that false floor, connecting all of the peripherals, the tape drive systems and the card readers, because you had to shuffle these computer cards with these columns and little holes in them and then run them through the card reader. And it was quite large. And those also tubes, partially, I guess at some point we started to use transistors, but tubes. And if you've got all these vacuum tubes which have lit filaments, little filaments, they're like little light bulbs, but they don't glow really bright. But they glow nevertheless, and of course that glowing, that little filament produces heat. So if you can imagine with some of the largest computers, thousands and thousands of these little vacuum tubes in a room, you had to have some heavy duty air conditioning as well. And not only that, but of course the problems of maintenance were enormous. Eventually the vacuum tube got replaced with the transistor, and we got even smaller and smaller and smaller with the transistor. There's a law called Moore's law, and that predicts that the miniaturization rate of technology gets. I don't quite remember exactly what Moore's law is, but it predicts smaller and smaller sizes, certain reduction of size every year or every 10 years, something like that. But it does, in fact, produce miniaturization. As you can see on this graph I've got here, we go from vacuum tube amplifiers to something that's in the palm of his hand. And in fact, I jumped quite a few decades in order to get to the going from left to right, because the transistors, even transistors, were relatively large and to some degree got hot, but they were just a huge improvement over vacuum tubes. And then later somebody said, hey, in fact, that later was an inventor, an engineer at Texas Instruments. And they said, well, why don't we put several transistors together on a chip along with their peripheral components as well, the resistors and capacitors, and now we can put an entire circuit on a chip. And that just got that technology expanded into the point where we can now put millions of transistors on a single chip, and hence you have today's central processing unit, or CPU, that's in all of our computers, our smartphones, to varying higher or lower degrees. The CPU operates as any so-called smart system's a central brain, so to speak. So whether it's your smartphone or whether it's your PC uh, or your laptop or whatever, there's a CPU in it, and that CPU has in it anywhere from thousands to tens of thousands to millions of transistors embedded in that silicon device. So we go now. The first issue was, like I said, miniaturization. How do we detect the signal? How do we amplify the signal? And how is it amplified in such a way that we can make this technology more available to not only the public, but just to, let's say, medical professionals that want to use this a technology for diagnostic purposes. And the next problem is what we call reducing the signal to noise ratio. Now, I'll make a little simile here, and that is, if you go to let's say, imagine yourself in a very crowded, very noisy football stadium. It's packed. People are cheering, yelling, lots of stuff going on around you, and you talk to your friend next to you, and you talk to your friend in a normal voice, maybe even you whisper a little bit. Although he's probably not going to hear you. You have to go up to the ear in order to have him hear you. Detecting an EEG signal and separating it out. Or in other words, let's say somebody is across that football field from you and they want to hear exactly what you said. Now, hearing what you said means that they would have to filter out and separate all the noise in the football stadium and direct that simply to what you said. So that is called signal to noise ratio. And the issue now is not only just now amplification, because if you amplify a signal straight from the scalp, you may very well have that signal in there. If you amplify a signal coming from the scalp and your gain or amplification, let's say, is 100,000, you're going to also amplify everything else 100,000 times. You're just not going to amplify the EEG signal. So you must have some way of knowing where the signal is, that is the information, what you want to hear versus everything else, which is noise. How do you separate the two? And that then became the number one issue in EEG technology and measurement. And that's where we are today. And we do that now, not only through, and that was done, by the way, that was done somewhat successfully, up to maybe 20, 30 years ago, somewhat successfully, until we are now into the somewhat advanced digital age, where we can use not only the electronic components and design circuitry around that function. Rather, we use computer technology and digital analysis to tell us which is signal and which is noise. And from that, and from the computing and from the ability to filter using digital technology and algorithms, we have a much cleaner and finer means in which we can separate signal from noise. So computer power, as I was saying, and this is me right there. Now, it's not really me, but it could have been me. I had a job just like that when I was 16 years old. The room almost looks the same with these peripherals around there, and me sitting there with the tape reels. You don't see the card reader. Oh yeah, there's a card reader right there where my cursor is. That's a card reader right there. So we go from those mainframes, and then we have gotten to, let's say, the 9th generation Intel core devices, and all of the wonders that we tend to take for granted with laptops and smartphones, and our ability to access almost anything and everything through the internet and through the digital intermediaries therein. So we are now at the point where we can do far more sensing, amplification, filtration, or in other words, separating out the noise from the signal. And the last point that I didn't mention yet, analysis. What is the if the waves that we are detecting, if the signals that we are detecting, what are they telling us? What is that? What information can we glean from that? And from that, we need very accurate, very complex, very fast analysis equipment. And that, again, falls in the realm of computing power. Computing power, signal processing, and analysis. So EEG. This is and these are three non-intrusive methods of brain imaging, so to speak. The EEG is the least expensive. Now you see this figure here with this cap on. That's an overkill as far as the number of electrodes that are on the person. But we're gonna learn about these caps. They're called called a 1020 configuration. We're not going to use them yet. Maybe sometime in the future we might. But at this point, we're going to use your Muse headband, which measures two very important points of your brain, and that is your frontal lobe activity, your medial frontal lobe activity, and your medial temporal lobe activity, and it's reference to a ground. So we're measuring left, right, frontal, left, right, temporal, and then those are all referenced to a single point, a single ground point. So EEG it's a time series analysis. We're going to look at what we call spectrum, power spectrum, and that is, so if this is frequency here, the x-axis is frequency, where we see that the greatest amount of power spectrum, that is the highest amplitude waves, are in the very, very low spectrum, low frequencies, and the higher frequencies we dampen out this way. So one thing you might consider is, well, let's say that you want to somehow, if you need to change the relative ratio of these waves, you could use perhaps, and this is what we're going to try to do as well, we could use some sort of a feedback or retraining process by which this power spectrum density curve is changed over time. Here we have what's also called a time frequency analysis. This is something that you can see very, very readily as we use Mind Monitor with the Muse headband, Muse 2 headband. And we'll also be able to construct power distribution and coherence analyses to an extent with another program that I will show you shortly. But that program you may or may not want to use. We'll talk about that later. But I'm using it for additional analysis and for additional show and tell. I'll show you that in a minute. We've got structural MRI, magnetic resonance induction. You've got DTI, which is another form of MRI, but instead it looks at rates of diffusion outside and inside of cells or neurons, and because of that, this process allows us to actually look at how nerve tracts are connected. This is a very valuable tool here, and it was just developed fairly recently. And then, of course, functional MRI tells you which parts of your brain are lighting up relative to what you're doing, thinking, and or feeling. So moving into now EEG, the trace on the upper graph shows a segment of an EEG recording, and we can decompose all of these waveforms into an analysis, like I said, a fast Fourier transform analysis that shows the composite of that. Think of your voice. Think of somebody singing. that's not a single tone. That's not just only a C, a D, an F, or whatever. Your voice and all the other sounds that you hear are composites of many, many sounds. Let's suppose that you took some sound that you heard. Let's say you said some voice like, hello today, hello, how are you today? And then you took that wave bite, and then you then analyzed it to find out what the concomitant frequencies are within that segment. And this is what we're going to do. If you look down here, you see that here's the fast Fourier transform analysis of this. So it shows where the waves, where those waves are, and what we see here is we see in this range we've got a very high level, and then we go down as we go higher and higher in frequency up to 200 hertz. And that is almost the absolute maximum of brain waves, up to about 200 hertz. And we don't see much there, but there's a lot going on there nevertheless. We see that the greatest part of it is down here, and then it tapers off. Now, in order to understand waves, we also need to understand that they are, in fact, electromagnetic energy. Now we are looking at waves that have a very, very, very low frequency, and conversely a very, 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 very long wavelength. The higher the frequency, the faster the wave goes, the shorter the wavelength. A wavelength is starting up, going back down, going back through the horizontal, going down, going back up, and then ending again on the horizontal. If you think of a sine wave, going up, back down, and then down in the negative region, then back up again from start to finish, that's one perfect wave. And we, without any tools or technology or anything, we see only the visible spectrum. We are only aware of the visible spectrum. You might be aware of slightly lower frequencies, and that is those frequencies that are below red here. You see red right here. So up in here in infrared, and that's where heat is. So you would certainly, you don't see it, but you certainly feel it, and you might see its effect on other light that's hitting your eyes. For example, if you're out on a road and you see the heat coming and you're driving along, let's say a desert highway, and you see the heat, the heat from the road is rising up those molecules from the road, or heating up those molecules, and they're rising, and you see the effect of the light being refracted, so that it looks wavy as you approach, as you go down the road. So you can see the heat from, or the infrared that is, through another source, but you're not really seeing it per se. Then of course you know about night vision goggles. That's where you can actually see infrared. Ultraviolet, the same thing. You can't really see ultraviolet, but if you were in that same era, where I was sitting, sitting there looking at the computer, and further out, you remember maybe black lights and black light posters. You poster on the wall, and you've got some very weak ultraviolet lights, and those ultraviolet lights would cause the posters to illuminate, phosphorescence, and in that case, in a way, you would see the ultraviolet light. But we really do not see infrared or microwaves or radio waves or ultraviolet light or X-rays or gamma rays. We don't see any of this, and we certainly don't see brain waves. So we are able to, our retinas, the cones and rods in our retinas are able to detect this very, very narrow range of ultraviolet energy. Now, of course, as technology is advanced, we can detect and see, literally, I mean, not see in quotation marks, all of this through our own technology. All of this we can see. But without it, this is what we see. This is where we are here, brain waves. And the frequency of these brain waves ranges from 1 to 120 hertz. You saw in the previous slide that I showed you that where is that? Here we're going out to 200 hertz here, but 120, 200 hertz, that's about as high as we go. Here you can see that the wavelength of light, of red light, is about 700 nanometers. And when as we go up and up, higher and higher in the spectrum, that is into areas, ranges that have faster and faster frequency, therefore shorter and shorter wavelengths, we move from about the 700 nanometer range to the 400 nanometer range and less. Now beyond that, these are very energetic, and light has energy, but make no mistake about it. It is energy, in fact, and so as the light, as let's say, for example, infrared or any kind of light, a strong light gets transferred into energy, can get transferred into kinetic energy, or that is the energy of motion. It can get transferred into potential energy, which is the energy where it's stored and then used later. That's potential energy. And it can get transformed into chemical energy. That's how photosynthesis works. It gathers the energy from light, and that hence is photosynthesis. It literally creates oxygen from using the energy from light. It creates oxygen and with the energy of light and carbon dioxide. Okay, so anyway, no more biology here today, but just simply to say that this is a very small range of electromagnetic energy. This is the only part that we can actually see with our naked senses in order to, but the rest of this we use technology. We're going up here now into these brain waves that go down anywhere from 1 to 120, even 200 hertz, but I want to show you the difference. Up here, as we move from high frequency to lower and lower frequencies, here we see 900, that means 700 nanometers. Now, let me point out that a nanometer is 1/1 billionth of a meter, okay? And a billion is 1,000 millions. 1 billion, 1,000 millions. So this is the wavelength, that is from start to finish of one of these waves, is 700, 800 nanometers. As we move down, and when I say down, I mean we are decreasing frequency. That is the number of times per second that the wave goes up and down fully. That's frequency. It's called hertz. Hz is the abbreviation, Hertz. So hertz otherwise means cycles per second. And in fact, that's what we used to say instead of hertz. We used to say cycles per second. But that's as we go into lower and lower and lower frequencies, we get longer and longer and longer wavelengths. Notice here, as we go from purple and blue light, we go from about 400 nanometers up to 700 nanometers. Now let me point out now that our brain waves going from this range of 1 to 120, that ends up being about 38 million meters, which is about 23,390 miles for I think I calculated that based on a 10 hertz alpha wave, and alpha waves are between 8 and 12 hertz. So your basic garden variety alpha wave is about, like I said, about 10 hertz, and it has a wavelength of 38 million meters, or 23,390 miles. So the electroencephalograph, as we know now, it records the electrical activity of our brain from the scalp. And the recorded waveforms reflect the cortical electrical activity. Now, It used to be in the movies. Let's see, what was one of my favorite where they used the EEG? That was, I hate memory blocks, but it had William Hurt in it, and he was in a sensory deprivation chamber, and they were looking at his brain waves all the time. And damn, I've seen that movie so many times I can't remember the name. At any rate, I'll think of it. I'm surely as you watch this, you're all yelling out, "Oh, I know that movie, and it's so and so." But that, as you'll remember, was on a large sheet of paper. So all those brain waves we saw on this going back and forth, there were pins going back and forth on this piece of paper, and the paper was rolling along. We don't do that anymore. Now we simply record the signals much more accurately and make those signals available for analysis of almost any kind digitally. So, but this is what it looks like. So gamma being the highest frequency, and those are those things that are going up to 200 hertz, the gamma ranges, and there are now 4 ranges for EEG: delta, theta, alpha, beta, gamma. Gamma being the highest range, which starts maybe at around 30, 40. It depends upon who you're talking to. But those are associated, gamma is associated with problem solving and concentration. Beta is just a busy, active mind. Alpha is more restful, mindful, reflective. Theta is a drowsy state as you're falling off to sleep. And then delta. The delta is a very deep sleep with very slow brain waves. So let's start and look at these brain waves singularly, and then as we move into the course and over the next 15 or 16 weeks up from the end of August into December, we are going to analyze our own brain waves eventually once we learn about just what the procedures are for measuring brain waves and the technology behind it. So when we look at signal frequency, these are the main frequencies of EEG now, from slowest to fastest. Let's start with delta. Delta has a frequency of about 3 hertz or below. So it is clearly very, very, very slow. Like if you were to tap your and do that 3 times per second, that is a 3 hertz signal. It essentially it's a beat. It sounds like a beat, going boom, 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 boom. So and this tends to be also the very highest in amplitude. So they are the slowest waves and the highest in amplitude. So if you're looking at a power spectrum, we see that delta occupies the majority of that spectrum simply because they have the highest amplitude. It is normal as the dominant rhythm as well in infants up to about a year of age. And it's also very prominent, as you will find out, frontally in adults and posteriorly in children. So you're going to see a lot of delta on your own brainwave spectrums, and you'll say, well, wow, I'm not sleepy or in deep sleep. Where's that coming from? No, it's always there. It's always there. What we tend to look at now, what we're looking at really are ratios, not absolutes. Theta is the next slowest, so we go delta, then theta. Theta is a frequency of 3.5 to 7.5 hertz. It's classified again as low activity, and it's normal in children up to 13 years and in sleep, but it is somewhat quite abnormal in awake adults. Then alpha, and this is the almost overrepresented frequency range. And the frequency range for alpha is 7.5 to 13 hertz. It's it's as far as brain anatomy is concerned, it's most seen in posterior regions of our brain on each side, and it tends to be higher in amplitude, though on the dominant side. So that means that if you are right-handed, your dominant side is probably your left side of your brain as well. If you're right-handed, you also probably have your major speech centers on your left side in your medial temporal regions as well, both Wernicke and Broca's area. Broca's area being forward to Wernicke's area, almost in fact in your posterior frontal lobes. When you close your eyes and relax, you get more alpha. And it is in fact the major rhythm seen in normal relaxed adults. With your Muse, now for our purposes and with this class, we're going to use Mind Monitor, and the Mind Monitor gives us ways in which we can look at all the frequency responses. And this is something that I do hope that all of you just play with and have fun with. But the Muse headband itself, with its own software, by the way, now its own software, that is a meditation software, and it is meant, its purpose, it is a software that is designed to do one thing, and that is to help you to get into and stay in longer alpha states, because the alpha state is in fact associated with calmer relaxation, and we use it in we could use it in other types of therapy, otherwise called mindfulness therapies. We can get into a bit of that later when we talk about how we can utilize EEG just in the treatment of certain mental disorders. It's become somewhat of a successful process, and in some corners of that, in some areas of it, it is quite well documented and has a lot of evidence-based research and therapy behind it. So we have alpha during most of our life, but especially after we go through puberty, basically. Then we get into beta, and beta is considered fast activity. It has a frequency 14 hertz and higher. It's seen on both sides of our brain. It's symmetrical. We see it on both sides of our brain. It's most prominent in our frontal lobes. We can accentuate beta by using certain drugs, sedative drugs, hypnotic drugs, benzodiazepines, or tranquilizers as they're called, lorazepam, something like that, will in fact increase levels of alpha, and I imagine, since benzodiazepines and alcohol have similar neurological action, in fact. And so I would imagine it'd be an interesting test for somebody here to do, if you want to, is to look at how your alpha changes over the let's say the amount of the number of drinks that you've had over a certain period of time. Interesting. I just thought of that just now. Somebody may want to pick up the gauntlet on that one. So beta is generally regarded as a normal rhythm. I've worked with some children who are, and adults as well, with very clear ADD, ADHD diagnoses. You can see it and assess it quite accurately as well. And using here's an area where EEG feedback has been demonstrated to be quite successful. Only instead of having let's say an ADD individual meditate and try to drive them into alpha, they've already got too much alpha. What you want to do is meditate them or feedback them into more beta. And this has also been demonstrated to be quite effective. And then last but not least, gamma. Now, gamma is above 25 hertz. Clearly, it is is a much higher frequency brain-wise, and we see that a lot in the temporal locations. It is associated with speech and memory processes. I've got memory there, but speech as well. Memory processes both long and short term. Gamma is also involved in attention and working memory. Now, attention and working memory, of course, is associated with higher and higher frequencies. So if you want to improve the focus and attention of somebody who apparently, through other types of diagnostic means, has insufficient focus and attention, you want to drive them more into the beta and gamma region. It is like I said, working memory, short-term memory, long-term memory, focus, attention. However, you also see excessive gamma activity involved in other types of psychological disorders. We see it in schizophrenia. We see it in Alzheimer's disease. We see it in epilepsy as well.
Different biophysiological readings, starting from sort of the crudest, the tin can e-meter that I showed you that uses, that measures, doesn't really measure it, it just shows galvanic skin response varying back and forth. Then I showed you the polygraph, not very good polygraph, but a polygraph nevertheless, and it showed you that when the galvanic skin response measurement is very secure, that you see a good, a steady line, and then when it does change, you can know that that change is due not to some sort of external artifact, but in fact to the change that it's measuring. In other words, it becomes a more valid and reliable measurement. But now we're going to go to what this course is really all about, which is electroencephalography, EEG. And we'll talk, of course, later in the course about the history of EEG as well as just the history of biophysiological readings to begin with. But I've got my Muse headband here, and I've been playing with this quite a bit before we started the course. And I'm going to show you a few things that I've learned about it. First of all, make sure that it's fully charged, and you attach the band. It comes with a little charging cord, and so you can little USB charging cord, and you can attach the you can set up the charge here at the end, right like that, and then plug it into a USB socket. I've already got mine charged up, so I'm not going to worry about that for now. But notice that also it's got these little retractable earpieces. Now this is measuring, this Muse headband measures 4 points and a ground. So those 4 points are frontal right, frontal left, temporal, medial temporal left, and medial temporal right. And for all intents and purposes for this class and our studies, that's enough for now. And that just gets us into working with it. But just with this, we can do some amazing things, some amazing observations, as well as some research. So let's start. So the first thing is you need to pull those out. This is supposed to fit on your head. And before you put it on, because if you forget this, then you have to take it off and do this again. Here's the on switch right here. Right, that little button right there. So you're going to turn it on like that, and then you're going to see those little lights flashing going back and forth like that. And now I'm going to just take this on. And the other thing is I usually take my glasses off to put this on, although you could use it with your glasses on, but put it on with the glasses on. I take my glasses off first, and then you sort of push these back like that and snap it into position. Now, you'll notice it's still a little loose back there. It's a little loose right here as well. And so what I do, like I said, I've been just sort of experimenting with things, is that I borrowed one of my wife's headbands, and I then use the headband to secure it even better by doing that. Now, you see here that it's secured, and in fact, it's even better if you put it back like that and make sure that it's good and tight. I also cleaned the forward electrodes, the contacts with a little alcohol. You could use a little isopropyl alcohol. I wouldn't put isopropyl alcohol on the rubber material here, though. It might corrode the material. I just used water on that. But on the metal, yes, I did use isopropyl alcohol. And then I just put my glasses over it like that. What we have is to go into the app. Now, there's the Muse app, which I'm going to let you play with by yourself when you get your Muse headband. And the Muse app is primarily for, in fact, not just primarily, it's totally for meditation. And, of course, using EEG and EEG feedback is an excellent way to practice, and it's certainly to get into meditation, because it gives you a excuse me, a reliable reading on your alpha level, and so as you push your alpha level up higher and higher, you go into a more relaxed and meditative state. But we're going to use another app called Mind Monitor, and I'm going to press Mind Monitor here, right like that, and you can see it's coming on, it's connecting to Muse, and as you see here, it's coming on, and you notice that if I jiggle the headband a little bit, that comes back on, that goes back off again. Excuse me. And the reason it does that is that it has to make sure that you've got contact on all all 5 points before it can get started up and present you with a reliable reading. So anytime that comes on, that's telling you during that period of time, the readings it's taking aren't particularly reliable. And you can see here on this screen right here that I've got all 5 ranges of my EEG, my waves going here, and that up here is delta, alpha, and then you see the purple line is theta, the green line is beta, and the orange line is gamma, and of course and then those are all up here in red as well. And we'll learn about how that works as well. But the main thing we want to do is once you get this and get this set up, and I'll give you another video on how you get this set up. But when you get this set up, you need to be able to also stream your EEG data to another program that you may or may not want to use. That it all depends upon you. But we can stream it, and we can also record it. Now, if you don't have this other program, you can just simply record your data. You see the little red record button, and now I am recording my data, and it is being recorded. And as long as I have that on, it is recording exactly what you see there on the screen. And so we'll be able to just do some basic research, doing certain things before and after a certain action. Like, let's say, for example, that you put it on and then you're recording it, and then you go and you read a book. So as you're reading a book, what happens? What changes between before time? Let's say you have it on for 5 or 10 minutes, and then you start reading the book, and then what happens afterwards? So we'll look at all those different things, and just simple things. Let's say you're in a dark room, and you've got your Muse headband on, and you're recording your brain waves, and then all of a sudden the lights come on, and the room becomes bright. What happens with your brain waves? That in and of itself is something that we want to look at, and the reasons for looking at that. Now I'm going to turn this recording on, and now it's zipping the file. It's zipping the file, and then it tells us that we can save the file. I usually save my files up to my drive here, so I'm just going to save that file. It's preparing to upload one file, and there it goes. What we want to do is this, or what I'm going to show you right now is something maybe a little, I think is interesting, but there's a little bit of technology and interface with your PC or your laptop or whatever you've got, and your phone. So first of all, you need to be able to stream your brainwaves via what's called an OSC stream. And you need to be able to find whatever your IP address is for that. And I've already got the proper IP address there, as well as your port, which is port 5000. So then you need your port at 5000, and make sure that this is set at 5000, and also your computer. And again, this is something that we will go over in later videos, and something that you're going to have to probably play with a bit, because if in fact you decide to stream your data, you can get through this course perfectly fine without having to stream your data and do what I'm going to do, but you're going to miss out on some of the fun in not being able to do that. But now the next thing I'm going to do is, you see here this little graph here, this little sharp graph spike. I mean, I can change with this and show you where, this is where all of the different points are. They're called TP10, AF8, AF7, TP9, and some of these other points. It shows that as well. I can hit that again, and that gives us a spectrograph. That is literally a spectrograph. Again, a little bit technical. I'll be explaining this further into the course, and also you'll be studying this as well. But this shows the relative spectrum here, where the side of where the theta is, and the delta is very high. And then as we drop down into the alpha and the gamma, we see that we have lower and lower total band energy, so to speak, or peak performance. Then we can go into that one once more, and as we move through time, as we're doing, we see here that where we have a lot of red, that's where a lot of the energy is. And then as you move from left to right, it shows up here the amount of total energy of the entire EEG spectrum being utilized from a lower wavelength, 8 hertz and down, all the way up to 56 hertz here, which is in the gamma range, and down below 8 hertz we're into the theta and delta range. This is interesting. This also contains an accelerometer, and again, once you get your system, yours will work the same as mine. But if, let's say I turn my head left and right, you see what's happening? That shows that that's an accelerometer. If I move my head up and down like that, you can see that, or left and right. So that's so that's a nice little addition as well. And then I'm going to go back to the standard waves, which is right there. But here's what I really want to do now, is that I'm going to go over here, and I am going to turn on right here it's called Neurovisual. Neurovisual, it's a nice little software app that you can download for free. You might have to play with it a bit, but I've got this, and it's quite cool. I'm going to also start to record the screen here so that you can get a better look at this as I talk about it. Now, I'm going to start to send that. It says now streaming, and it says I'm streaming, and it tells me that where I'm streaming, and it is in fact going to the to my PC right here. And if I press the streaming button, you're going to see the stream that's from here as well. And we are, of course, recording this, but you can get all kinds of interesting images here. For example, on the screen, I've got here not only the actual EEG band. Now, when you see spikes like this, now that's a delta spike, and it just spiked way up and then dropped off. These spikes aren't, this is artifact. This is a measurement artifact. It's not real. It meant that something happened at the contact. And so sometimes it's better that we just look at averages, like relative percentages. Now, see, so there we're starting to see now relative percentages. And what's interesting is if you go over here, this also shows you the relative percentages being used, delta is about 39, 40%, theta, alpha, and beta and gamma, a very small percentage of gamma, which is considerably higher even than beta. But you can see how this is changing as I talk. And marvelous different experiments can be done here as well. And right here is an actual brain map, which we'll see as well. So the brain map, which is I'm just recording the screen here, shows you not only the different bandwidths or bandwidth ranges like delta, theta, alpha, beta, and gamma. It shows you not only that, but then remember that we're looking at 4 spots. We're looking at frontal and medial temporal, and so it's showing you where those are relative to what we are observing on the phone screen as well. So, and in fact, you could almost just put the phone screen aside, and then we can just look at the map itself. So there's marvelous things that we can do with this. We can also collect data using this as well, and we can do something else here. We can look at raw EEG voltages, which is considerably different. We can look at left-right, and this shows you the ratio between what's going on with your left hemisphere and your right hemisphere on your front, or your temporal, your frontal lobes, as well as your then your ears, your temporal lobes. So frontal and temporal, and it's showing you the ratio here as well. So again, I am streaming, and I can also record on here. And so as I record, it is recording exactly what I'm doing. I can put, again, the relative percentage. I can use linear values here, linear decibel, dB decibel values, relative percentages, raw EEG voltages, and when I'm using raw EEG and raw active sensors, I can turn these off and on. Let's say I'm only interested in the temporal, then right now what we're looking at is only temporal from left and right, or I can turn the temporals off completely, and now it's stopped, of course, and I can turn on the, so now I turn that back on, and now we're seeing only the frontal lobes on both the left and the right.
Now, I do hope that this little presentation that I put together here, because I'm sort of piecing together all different types of things in order to give you a good snapshot of what we're doing, and I hope it is my sincere desire that this has gotten the idea across. Naturally, we're not face to face. We're not physically interacting. I think if we were at the intensive, I would have brought some of this equipment with me, and we would have done show and tell right there in the classroom with everybody else, making fun of the participant, the brave participant that we would have used otherwise. But I'm looking forward to getting into this a lot deeper during the course, and some of you I recognize on the roster. You've been in my classes before. A few of you, I think we've studied quantitative research methods together. We've studied some basic introductory statistics. I think you've taken my course, some of you, in biopsychology. And so now this is the fourth course that I think some of you may have taken all 4 with me. And this is the introduction to EEG. After this, you may be interested, very much interested in extending this even further into doing some real research. And I see this as potentially broadening the scope of transpersonal psychology in looking at some of the tenets there and seeing if, in fact, we can detect that which we believe to exist. How can we detect those things? And so it will be up to you, the graduate students and future academicians and researchers, to go and use these tools to indeed make some of these determinations. I think this is the end slide. Let me see. Nope, there's more. Yeah, there's a lot. Oh boy, there's a lot more. So EEG cables, this shows the electrodes, the disc electrodes here. You can see these little discs. There's the end right there. These would go into the amplifiers, the EEG amplifiers. This is a cap that we're not going to be using, but we will talk about how it's used. We'll talk about how to use it. We will discuss its essential or its basic configuration, which is called the 1020 configuration. But in this, these electrodes are embedded into the cap, and we can do high density arrays and measure a lot of different points relative to brain anatomy by using these electrode caps right here. These electrodes are inside this cap. You can see the cable, the ribbon cable going off here, and these are points in which we make contact. We inject electrode gel into these. I think that I've got on your agenda in the next couple of weeks or 3 weeks, even a video of how the gel is introduced into these. We're not going to do that either, but again, this is something that you need to know in order to do real, actual. We're doing real EEG with this course, but I'm talking about the more advanced version where you can do some exciting research as well. So the electrode gel that I mentioned, it is essentially an extension of the electrode, and it makes it so that we can make contact with the scalp. And I mean, if you think about it, you can't just shave somebody's head whenever you want to do use the electrode cap and to make contact with the scalp. So how do we do that? Well, we do it by using the electrode, then we also use electrode gel. And the gel, of course, maximizes the skin contact and also provides for a lower resistance recording through the skin. And I say resistance there, that is technically not really incorrect. It's something called impedance, which is sort of a resistance. And that is a measure you might encounter as if indeed you are still continue to be interested in electroencephalography. Something like impedance measurements are important as you move forward beyond this. But this gel is injected into all of these cavities. Electrode positioning, as I mentioned, is this 1020 system, and it is the standard placement for scalp electrodes in classical EEG recording. But the essence of it is not so much in the exact position as it is in the percentages of distance going from this point called the nasion, right here, just above the nose, right above the bridge of the nose, all the way back to the inion, which is right at the base of the head. So that distance needs to be covered. So you go nasion 10% up. Okay, first electrode, then 20%, 20%, 20%, 20%, 10%. That's why it's called the 1020 system. 10, 20. 10%, 20%. Then the points are then marked relative to the lobes to which they are associated. Frontal, central, which is primarily the reference or ground points, the parietal lobes, the occipital lobes, and the temporal lobes. And of course, like I said, the midline or central electrodes are marked with the subscript Z, standing for 0, and those again, like I said, are the reference points for it. So we're going to look at other things called montages. Now we're going to become even a little more advanced in this process. So how do we, when we place the electrodes in a certain way, we get different kinds of data. So they can be monitored with either what we call a bipolar or a referential montage. The bipolar montage or the bipolar referencing system means that you've got 2 electrodes per channel, so that you have a reference electrode for each channel. And that's a lot of electrodes. But in that, you have extremely accurate readings because you're measuring. Again, each measurement is referenced to that channel which is being measured, as opposed to a referential montage, which means that each point that's being measured is referenced to a point that is further or closer away. So if you're measuring, if you've got some reference point, let's say in the middle of the skull, let's say in here somewhere, each one of these points is being referenced to that. So whether it's close or far away, that's the reference point. The other issue with EEG technology and EEG is what's called the EEG artifact. It is one of the biggest challenges with monitoring EEG, and that is the artifact, being able to recognize it and being able to eliminate it. One of the major problems with EEG research is EEG artifact. People will put a lot of time into some research project, and they don't take into consideration all of the possible artifacts associated with EEG. Remember, you're measuring voltages from the scalp that are in the microvolt range, the millionths of a volt range, amplifying that thousands of times, and then trying to separate out the noise from the signal. Where else can you get noise? Given that you've got a millionth of a volt reference anyway, you could pick up a millionth, you can pick up more than that just on a wire with transient radio waves all around you. So it is very important to realize the ambient electromagnetic environment, and that is something that I've seen all too often. People doing research in this area, they don't take that in consideration, and then they'll see some artifact, probably artifact, because they haven't taken the necessary steps to recognize and filter out confounding artifacts. And they'll say, oh boy, look at that, we've got some significant results, and they don't. There are patient-related artifacts: movement, sweating, ECG, eye movements. There's technical artifacts. You've got 50, 60 hertz all around you, just from the wall. Cable movements can create artifact. Electrode paste-related artifacts. Everything has to be taken into the. Remember, again, tiny, tiny, tiny voltages. So we have to be very, very, very careful in our measurements. We have some tools for finding artifacts. Impedance, like I mentioned to you before, is one of the important tools for measuring contaminated signals. So we're going to take that in consideration. Not a lot in consideration right now, in that we're just looking at it. We are indeed an introductory course, so we just need to figure out what it is and how to do it. But there's all kinds of other things to take into consideration if you're actually going to do research in this. And if you look at various parameters on the monitor, you can actually see where there's interference and electromagnetic or physical artifact as well.
The hardcore, how do we make sense of this? How can we do research so that we can answer some of the questions that any of you might have as far as how can we use this tool to answer the questions that we want to answer? And so in this next 15, 16 weeks, that is the fall semester here at CIIS in the transpersonal psychology program, what can we learn and how can we propose, that is operationalize and then propose research where we go beyond just this for contact frontal lobe and temporal lobe measurement into the full 10-20 system, which of course you will learn later as well. So I do hope that that at least gives you a preliminary idea from what we're going to do in the next semester. I do wish that I could have shown all of this to you in person at an intensive. Of course, that isn't possible, and I do hope that we're all staying safe and healthy and sound in our homes right now, or wherever you are. But I think we're going to have fun with this, and so that's how. That's about it for what I've got to show you as far as just these impromptu videos, and I hope to see you all in January. Maybe we can all get together in January. So at any rate, adios, auf Wiedersehen, goodbye,
Tschüss.
tschüss.